Oh yeah. Okay. Thank you. Can everybody hear me? Okay. Okay. It seems like I got the question already. Should I check that or? Okay. So I'm Andres Izidoro. I'm an assistant professor at Rice University. For those who don't know where Rice is in Houston, Texas. And I'm going to talk a little bit about terrestrial planets. And when I was preparing this talk, I didn't know if I should focus on solar system or if I should focus on exoplanets. And I decided to combine the two things in a single talk. And hopefully, it's not going to be too much for a 30 minutes presentation. So to start, I have selected these two iconic systems of terrestrial planets. Probably my pet systems if I have to pick two of them. So that is like the TRAPPIST one, and of course, the solar system. And these planets, they might have some similar, maybe composition, maybe mostly rocky, but they might have formed in a very different way. And in this talk, I'm going to show you how we think these planets form today. So to start, let's just figure out what the Earth is. Earth is not just a single planet with one Earth mass at 1 AU. We know that the Earth formed over a long time scale, probably something between 30 and 100 million years after the formation of the solar system. And we know also that Mars, for instance, was a planet that formed much faster, probably was completed in about 2 to 4 million years. So we know from the solar system that these small planets or Mars objects, they did not migrate too close to the star. They probably stay near where they are today because migration is not so important for small planets. I'm going to talk more about this later. But the question that I'm going to ask here today is, what can you tell about terrestrial planets that are slightly more massive than the Earth? So to start, I'm going to just briefly review the stages of planet formation. We know that planets form in disk of gas. Planets grow from sized dust grains that stick together and form what we call pebbles. Pebbles are millimeter to centimeter sized particles that drift inwards by gas drag. So these pebbles, we believe that they eventually concentrate at some specific regions of the disk, and they essentially allow the formation of planetesimals. Planetesimals are kilometer-sized objects. So planet formation essentially jumps from something that you can hold with your hands to something that's much bigger than the city. From that point, we might bifurcate in two different growth types of growth. We can grow by accreting other planetesimals, that's what we call planetesimal accretion, or planets can further grow by pebble accretion. Essentially, planetesimals accrete small drifting pebbles. And these two processes might lead to the formation of what we call planetary angels, objects that are about moon mass in the inner parts of the solar system, maybe Mars mass. So these objects, if the gas is still around, they might further grow to bigger planets, even gas giants in some cases, and they might migrate depending on their masses. So when the gas goes away, so these objects in the different regions of the solar system might experience giant impacts and might form final planets. So to start, just to understand how terrestrial planets form, I'm going to pick the solar system first. Here's a picture of the solar system today. Just a final one of this kind of part of the solar system. We have the 4 terrestrial planets. We have the asteroid belt somewhere here. Maybe you cannot see let's use the pointer. The asteroid belt, and we have Jupiter. So we know that we have in total mass in the inner terrestrial planets about 2 Earth masses of solids. The asteroid belt region is very low mass. And the asteroid belt is a mass of objects with different colors and probably different compositions. So when we model solar system formation, we have to match a few constraints. We have to explain why we have maybe 4 planets, the masses, the orbits. We have to explain their growth timescales. And also, you have to explain why the asteroid belt is so mass depleted, why you don't have much more mass in the asteroid belt today. So we also have to explain why we have this dichotomy in composition of asteroids, essentially what we call S-complex or C-complex type asteroids that are asteroids that we think that form in the inner and outer parts of the solar system. And we also have to explain the orbital distribution of asteroids in the belt. These are constraints that a successful model of solar system formation has to match. To start, we know probably you have seen this cartoon before, this animation by Sean Raymond, modeling the formation of solar system in the classical scenario of planet formation. Here we have Jupiter fully formed. There is no gas in the disk anymore. So you have a distribution of planetary objects from about Mercury's location to close to Jupiter. The colors don't really matter in this point. But if you play the simulation and you run the system, you let the system evolve for hundreds of millions of years, what you end up getting is a few planets that looks like the solar system. But these simulations have a classical problem. So after several hundred million years, we end up with planets around 1.5 AU, much more massive than the Mars. So typically 10 times more massive. So that's what we call the small Mars problem. So if you let the simulation evolve enough, we can see now we have one planet that looks like the Earth at 1 AU, maybe something that looks like Venus, and maybe something that looks like Mars. But we can see that Earth and Mars in the case, the mass indicated by the size of the dots is not that different. So Mars in this case is about 5 to 10 times more massive than the real Mars. So this is the small Mars problem in the classical model of terrestrial planet formation. So how do we solve the Mars problem? Today, we have two main solutions. We have probably 5 of them. And we have the model called the low mass asteroid belt model, the pebble accretion model, the convergent migration model, the Grand Tack model, that's probably the most famous of all of them, that was proposed in 2011. And you have also the early stability model. All these models rely on a simple point. In order to produce Mars, you have to deplete the Mars region early enough. So the low mass asteroid belt model proposed that the Mars location was born empty or virtually empty. So Mars is naturally small. The pebble accretion model, I'm going to talk more about these different models in a bit. Actually, let me go to this slide first. So the low mass asteroid belt model proposed that terrestrial planets form from a narrow ring of material around 1 AU. In the asteroid belt region, we have just a few planetesimals, or maybe even was completely empty. And you had a lot of mass in the older solar system where the giant planets form. So this idea is inspired by this recent ALMA observation suggesting that, young protoplanetary disks, they show these ring-like structures. And this is potentially consistent with the idea that planetesimals form at specific location where we can concentrate dust to promote planetesimal formation. So one idea is that maybe the terrestrial solar system formed from 3 rings of planetesimals. One ring of material was located around 1 AU. The total mass in this case is about 2.5 Earth masses. There was a second ring of planetesimals of material beyond 3, 4, 5 astronomical units where the giant planets formed with a lot of mass, perhaps almost 100 Earth masses solids, and maybe even a third ring beyond 20 or 30 AU that be consistent with the primordial Kuiper belt. Several models of solar system formation actually propose that the terrestrial planets, the solar system did not form from a smooth distribution of mass, but from maybe multiple rings. So in this model, the terrestrial planets are created from the inner ring. Mars is small because there's no mass for this planet to grow around this location. And then the asteroid belt is populated by objects from the inner and outer solar system. And that might explain the dichotomy in composition that we see in the asteroid belt today between S-types and C-type asteroids. So the pebble accretion model proposed also that terrestrial planets form in a very narrow ring, but this ring was essentially fed by pebbles that was drifting from beyond the snow line. And in this model, planets grow by slowly accreting pebbles in a way that they do not migrate that much to become super Earths. if there's a lot of pebbles drifting inwards, the terrestrial planets grow faster, and they eventually migrate to the inner edge of the disk, becoming perhaps super Earths. So the pebble accretion model relies on slow migration of the planets associated with a very controlled pebble flux. So the planets grow and migrate inwards. So finally, the convergent migration models propose that, so there was a lot of mass in the inner solar system, maybe similar to the classical model. And then these embryos, they migrated towards 1AU, towards a trap, a convergent migration zone. So that region around 1.5U where Mars was growing was depleted by migration, and the planets eventually formed. Finally, the grand tack model, we have Jupiter migrating and truncating the terrestrial planet disk, creating a Hansen-style disk that also leads to the formation of a small Mars at 1.5 AU. And as the last model, the early stability model proposed that the giant planets in the solar system, indicated here by these 5 dots, Jupiter, Saturn, an extra giant planet, Uranus and Neptune, they had a dynamical instability in the past. And that dynamical instability scooped that region around Mars location, producing at the end a small Mars. So we have all these different solutions to explain how the terrestrial planets form today. And in order to distinguish them, we have to better understand how planetesimals form and where they're formed. Maybe some of these models could work together, but maybe in the future we might reject some of them. Now, this ends essentially my first part of the talk, where I talk about solar system, and now I'm going to talk a little bit about this super Earths and mini Neptunes. Here's a plot showing some selected systems of super Earths and mini Neptunes. So we have the name of each system indicated in this column. So we have, they are plotted in function of the period. So each line shows one planetary systems, and we show the solar system down here just for reference. And when you look at the systems of super Earths and mini Neptunes, super Earths are planets with sizes between 1 and 4 times the size of the Earth. That's how we usually define them. And so we know that super Earths and mini Neptunes, they are very common at orbital periods shortened than 100 days. They probably orbit at least 30 to maybe 50% of the solar type stars in the galaxy. Many super Earth systems come in multi-planet systems. We don't have just one super Earth, but multiple of them, as we can see here. They are compact, but these systems are not resonant. So planets are very close to each other and very close to the star, but they are not in a resonant configuration. I'm going to talk more about this later. And we believe that the innermost hot super Earths are probably rocky because we have mass and determined by TDVs and radial velocity, and also trans observations. So how do we constrain these models of planet formation? The first constraint, that's probably the most important one, is the period ratio distribution. In gray, I show the period ratio distribution of planets observed by Kepler with sizes smaller than 4 Earth radii. As I mentioned before, we don't see any preferential pileup at specific locations. For instance, like the 2-to-1 mean motion resonance that will be here. So the distribution of the period ratios between planets is quite spread. If the planets were in resonance, that's what we should see. They should pile up, maybe at the 3-to-2 mean motion resonance, or maybe the 2-to-1. But it's not what we see from observations. And this kind of pileup is that what we expect from migration in a gas disk phase. So what's going on? How do we explain this if planet migration is an important effect for planet formation? So another important constraint that we have from observations is that we call the exoplanar radius value. The exoplanar radius value is essentially a lack of planets with a given size of about 1.8 Earth radii. As you can see here, we have a plot showing the number of planets as a function of size, and we can see that there's a lack of planets with size about 1.8. Oops. We can see here in a different plot that's essentially orbital period versus size. that also this exoplanet rate value appears at this location right here. So planets are mostly about 2 point something Earth radii and about probably 1.3, 1.4, 1.5 Earth radii. How do we explain these observations in formation models? We also know that planets in the same systems, they typically come with the same size. That's what we call peas in a pod trend in the exoplanet data. So we can see here, so that if you plot the size ratio of planets in the same systems, the ratio peak is at around 1. That means the planets have essentially similar size. Okay, for the solar system, planets did not migrate that much, probably because they grew slowly and they did not reach the inner edge of the disk where we should have super Earths. But if planets grow fast enough, they migrate. And more massive planets migrate even faster. So if here is just a cartoon showing what happens. If you have planetesimals forming everywhere, maybe there's no line at some point here. These planets might grow by drifting pebbles. Planets growing beyond this no line grow faster because pebble accretion is more efficient. And then they start to migrate inwards. And then if they migrate inwards, they eventually park at the disk inner edge in what we call a resonant configuration. Here, the planets, in this cartoon, the planets are envisioned to evolve in the 4-3 mean motion resonance, 3-2, 2-1, and 4-3. Okay, but we know from the first constraint for exoplanets that Kepler planets do not pile up in resonance. So, but after the gas is gone, so these systems, they become dynamically unstable, and these essentially break the resonances and might be consistent with the architecture of planets that we observe today. So planets in resonance are rare today. We just have a few of them, maybe less than 10. And as I mentioned earlier in the talk, one of the iconic ones is the TRAPPIST-1 systems, where we have what we call a resonant chain. Here's a picture of the TRAPPIST-1, and these systems in a chain of forms of chain of resonances given by this architecture. Planets are essentially in the 3-2, 3-2, 4-3, and 2-2 mean motion resonance. We have other examples, for instance, TOY 168 and Kepler 223 that are other examples of nice systems of resonant chains. But resonant chains, they are very fragile. So if you just slightly kick the systems, you break the resonant configuration, as I showed before. And some of the systems actually, they naturally become unstable after the gas dispersal. But the TRAPPIST-1 is actually one of them that did not. We know that because we observe it today. So here's a simple experiment showing you what happens when you just kick the planets in the TRAPPIST-1 system. So here's a plot showing the instability time, how long the system takes to go dynamically stable when we allow the systems to interact with a given amount of mass. So here is the total mass that the system is able to interact with. Essentially, the amount of mass varies from 10 to minus 3 Earth masses to about 1 Earth masses. This is the experiment that we do. And we throw one single planet in the system or a planetesimal and see what happens. So we can see that if there's just tiny perturbation, very little mass, interact with the TRAPPIST-1 planets, like maybe some asteroids that were crossing the orbits of the planet that we cannot observe today, the systems tend to become remain dynamically stable, forming a resonant chain up to about moon mass. If you allow the system to interact with more than one moon mass of material, the systems become dynamically stable. This shows the instability time. The stability time decreases. So essentially, the systems spread and have giant impacts. So we know from this observation that the TRAPPIST-1 system migrated inwards, form a resonant configuration, and the systems over the last billions of years did not interact with more than one moon mass of material. Otherwise, would have become dynamically unstable. So from this observation, or from these numerical simulations, we can conclude that the TRAPPIST-1 systems form fast and probably wet. because we have from some interior models today, the TRAPPIST-1 might have, some of the TRAPPIST-1 planets might have water. So if this water is there, it was delivered early during the gas disk phase when the planets were still migrating. Okay, so let's go back to this big picture of super Earths and mini Neptunes. I show at the beginning of the talk, so the period ratio distribution of exoplanets here in gray. So I also show that if the planets are in resonance, they pile up. They show like as this head curve. If the systems become dynamically stable, they are given by this blue curve, the period ratio distribution essentially. So how do you match this gray curve? So we have systems that are in resonance, systems that became dynamically stable eventually after the gas dissipation. So if you mix a fraction of unstable systems with resonant chains, we can match this gray curve. So here's a statistical test showing that. And this statistical test essentially shows that if you mix a fraction of about 5%, maybe 3% of the head systems with the blue systems, we move the blue curve towards the gray one and we match what we observe. So this essentially shows that, suggests that most of the planetary systems that we observe today, they were resonant chains in the past, and they become dynamically unstable after gas dispersal. That's what we call the breaking the chain model. Okay, what this model predicts for the composition of these planets? And it predicts many things. So model A is essentially, I'm not going to go into the details of how model A works, but if you tweak the parameters, we can get systems that are essentially rocky. All the planets are rocky, essentially. So you can see here's the every line shows one system. The size of the dot shows the mass. The color shows the water mass fraction or ice mass fraction. And you have here this semi-major axis. So you can see for the color that for model A, most planets are rocky. But if you change the parameters, for instance, the pebble size, that's what we get. Blue planets, that means water-rich planets everywhere. But then if you tweak it again, that's what we get. Model C is a mix of rocky and water-rich planets. So depending on this, where planetesimals form, depending on the pebble size, we can get a mixture of different types of planets in the same system. So, and how this model matches what we call a radius valley and the peas in a pod. So here's what we found. So the top two panels shows the match to the radius valley shown in gray, and the peas in a pod also in gray here. So we can see that if planets are mostly rocky, as in model A, we don't see the radius valley. So there's actually an excess of planets at 1.9, 1.8 Earth radii. Of course, we match the peas in a pod approach. We can see that the size ratio peaks at 1, which is quite nice, but we don't match the radius valley. If you look at the same thing for model B, that are essentially water-rich worlds, the peak is at 2.6. We match again the peas in a pod, but we don't match the radius valley. And finally, if you have a mixture of systems with rocky and water-rich planets, we see that we can have a peak of planets at 1.3, 1.5 radii, a lack of planets at about 1.8, and again, a peak at 2.5. And again, we also match the peas in a pod. So how this model can match this dynamical architecture of the planets, but the only model that can match the radius valley and the peas in a pod as well is the model where we produce rocky and water-rich worlds. So here's just the final outcome of the systems. Here's the outcome of the model. Again, each line shows one simulated planetary system. And you can see here the observed systems color-coded by some size correlation. And, it's not that bad. Some of the systems looks quite nice. And, we can associate into this cartoon some of these nice analogs like Kepler 36, I think this is the one. So we have two planets with very different densities. as we do have this Kepler 36 analog. And also, we have like one potential analog of TOI 16878, I don't remember, where planets have alternate densities. We have a rocky with a hydrogen helium planet and another rocky planet. So here's just a summary of this final compositions of what we predict for the model. I'm going to skip that. And okay, this model matches fairly well the Peter ratio distribution, radius valley, peas in a pod. But what can you say about planets at 1U of sun-like stars? And the green zone here shows planets that we expect to form in this model at 1U. So the size of the dot shows the mass of the planets. And you can see that many planets are actually big and water-rich. But we do see some planets that are potentially rocky, like this one, but they are typically probably a few times more massive than Mars. It seems tricky to get like Earth mass planets in this model at 1AU at this point. So, but this is still work in preparation. Maybe things might change in the future, but I decided to show this here because I think it's really cool. So, just stay tuned. More to come. So just to summarize, so there are at least two types of terrestrial planets: those that grow like the Earth, slowly, and those that grow really fast, like the TRAPPIST-1 planets. And we have multiple models to explain how the solar system formed today, and we need to find a way to distinguish them. And hopefully that's going to happen in the next maybe 10 years. Only a fraction of the planets survive as resonant chains, like TRAPPIST-1, Kepler 223, and TOI 178. This model called breaking the chain is broadly consistent with the Peter ratio, the planet multiplicity distribution, the exoplanet radius valley, and it also suggests that super Earths, the innermost planets, are rocky, and probably the mini Neptunes are water-rich worlds. I think I should stop here, and hopefully I will have time to take some questions. Thank you.
All right, thank you very much, Henri, for this great introduction starting to the week. I think it set us up very well. I think we have time for, let's say, 3 questions before we need to move on. So I think we start over there first. Joanna Heske, please.
Yeah, thank you.
You can, there's a microphone in front of you. Just in front of you, actually.
All right, thanks for that.
I think it's fine, just
okay.
Yeah.
Thank you. I had one quick clarifying question and one larger question. In one of the classes of the Model T, the sub-Neptune histogram was higher than the observed frequency. So is that due to the sub-Neptunes that some have hydrogen atmospheres and some don't? Why was your prediction, I think, such higher?
It might be because of that, or might be just because we are producing too many water-rich worlds.
Okay.
It might be, yeah, both, yeah. You're right, yeah.
And the second question is, for that model that you're using to predict the 1AU planets, what does it predict for much farther out, like Jupiter and?
So we don't include Jupiter analogs yet in the plot. That's something that we're going to do in the next few years. Thank you.
Second question. Then how?
Yes, I was wondering, I guess your model counts to reproduce the dependency of the radius valley with orbital distance. Is that right? Or would you investigate?
We did not look into that yet. So with this new simulation that I just showed at the end, we are looking to this to see how it does. We're going to do that. Thank you. Yeah. That's a good point.
Quick remark, when you use the microphone, there's a button you need to press. So while you talk, you press the button.
No, just one.
Just one. Is there any last questions before we move on to the next talk? Oh, I'm sorry. That's
So my question is, in my slide, you show the model where you have the different cavities and the solar system. Do these cavities correspond to the giant planets, or are they more, fine-tuned?
We don't know. So, we kind of envision that, this
the model, where they put where they stochastically.
Can I just move back? Oops, I think I moved too much. You're talking about this one? Okay. No, this is just just a cartoon just to motivate the idea of having this planetasmos forming at specific locations. But in the model itself, we do not model in this slide here, we show these 3 rings. So that might be associated with these bright regions here, but we do not model the giant planet growing in this location yet. So that's something that we have to do in the future. Yeah.
Okay, so for the sake of time, let's move on. So let's thank our first keynote speaker again.
And our next speaker is Wolf Kuiper, who's from the University of Duisburg-Essen. The screen is yours once everything is okay.
Yes. You're first. Works. Thanks a lot for having me here. Yeah, and thanks, Andre, for setting the stage so nicely. So the research question for this